Now, there are a few things you need to be careful when we're dealing with limits at infinity. Okay, when you're dealing with limits involving negative infinity, you have to be careful with the odd powers. When you evaluate with an odd power, remember we're going to get a negative because an odd number, a negative number to an odd power is going to be negative. Now, you also have to be careful about calculations with square roots. So those are just two reminders to think about as you're dealing with that. Next, another thing that we can do to simplify these things is substitution. And that's where we want to try and remember these limits that we learned in 2-4. As theta approaches 0 of sine theta over theta, you get 1. And as theta approaches 0 of cosine theta minus 1 over theta equals 0. Now, these are not two formulas that I would expect you to memorize, but they're ones to keep on the side of your notebook as you're doing your homework. And I would give them to you on a test or a quiz, so I wouldn't worry about that. But let's take a look at our next example. Okay, in example 6, they want us to evaluate this limit. Now, please notice, this is sine of something else. So what I can do is use a substitution and investigate what's going on at 1 over x as x approaches infinity, and then figure out what's going on with sine as x approaches that value. So let's take a look. Okay, so what I'm going to do is I'm going to put a variable in for 1 over x. I'm going to say that it's t. So as x approaches infinity, t is going to approach 0 because remember, this approaches 0. Okay, so what I'm really looking at is the limit as t approaches 0 of sine of t. Now, sine of 0 is 0. So this whole limit actually equals 0. Let me say that again. Okay, so I replace this 1 over x with a t. Let me do it. Here's t. And I looked at what happened as this approached infinity, as x approached infinity. This t is going to be 0. So I'm going to change my limit to be as t approaches 0 of this thing. Now, sine, you can do sine of 0, so I can just plug this in and see what I get. Sine of 0 is 0. So my actual limit is equal to 0. This is my final answer. Okay, let's do another one. Okay, in example 7, they ask us to evaluate the limit as x approaches infinity of the sine of x. This is much easier if you look at a graph of what the sine of x is doing. So I'm going to put a graph on here of that. And notice what's happening with the graph of sine. It goes to +1, then it goes to -1, then it goes to +1, then -1. As you keep going to the right, it's always just going to be bouncing between those two values. So this limit does not exist because it's always bouncing between positive and -1. So this is D and E, does not exist. Okay? Let's take a look at more limits. Example 8 says find the limit as x approaches infinity of x cubed and the limit as x approaches negative infinity of x cubed. Now, if you remember what a cubic graph looks like, it will really help you with this. So I'm going to bring up that graph. Okay, so notice what's happening. As x approaches negative infinity, that means as I go this way, the graph is going downward forever. So that value is negative infinity there. As x approaches positive infinity, the graph is going upward forever. So this value is positive infinity. Let me show you what that would look like. So this is my final answer. As x approaches positive infinity, x cubed approaches infinity. As x approaches negative infinity, x cubed is negative infinity. Now please note, infinity is not a number, it is a concept. So we have to be really, really, really careful when we try and do operations with infinity. So let's take a look at some guidelines for that. Now, most operations, you can pretty much be okay working with infinity. I mean, they're weird, but they kind of work. But you can't do infinity minus infinity. That's not allowed ever, no matter what. It's what we call an indeterminate form, meaning that it can't be done. And you can't do infinity divided by infinity. Also not allowed. Okay? And the thing is to think about where the infinity is. So like if you have infinity divided by 2, that means it's just still going to get really, really big and it's going to approach positive infinity. If you have 2 divided by infinity, well, that's going to get really, really small and it's going to approach 0. So it's about thinking about where the bigger number will be and then figuring out whether it's going to approach positive infinity, a negative infinity, or some other weird number. Okay, so let's take a look at a few examples of this. Okay, so example 9 says, find the limit as x approaches infinity of x squared minus x. So notice what's happening here. You have a really, really big number squared minus that really, really big number. Now, because this is something squared, it's going to dominate what's happening here. It's going to make it just a really, really big number. Okay, so sometimes it helps to think of it in terms of like 100 and figure out what's going on there. This would be 100 squared minus 100. And then think about like 1,000 squared minus 1,000. And think about what's going on here. In this case, this is going to grow forever. So this limit is actually infinity. Okay, and this is my answer, is that this limit equals infinity because this is growing faster than this. Let's take a look at another one of these. Okay, so looking at what's going on here, notice we have x squared plus 1. We've already investigated that you have infinity squared plus another infinity. Well, that's just going to get you a really, really, really big number. And this is going to grow much faster than our denominator. But one thing to watch out for is that this is minus infinity. Okay, so what that's going to do is this is going to be like a really, really big number divided by a negative number that's smaller than it. Okay, so it's going to actually end up giving us negative infinity as a result. Okay, and you can kind of think of it like ignoring this 3. The 3 is so small compared to these really, really big numbers that they don't really like make a difference. And then you could probably just reduce this by x and you get like x plus 1. But remember, there's a negative sign down here. So it's really negative x minus 1. Okay, and that gets you negative infinity. Okay, so what I did is I completely ignored the 3 because it's so small it doesn't even matter here. And then I said, well, it's kind of like this. And I reduced this by x, and I dealt with the negative sign to get this, which is going to approach, as x gets really, really, really big, it's going to approach negative infinity. Okay, we have one last example. Okay, so we're given this example. It says sketch the graph of y equals this function by finding its intercepts and its limits as x approaches positive infinity and x approaches negative infinity. So the first thing we're going to do is find its zeros. We have a 2 with multiplicity of 4, negative 1 with multiplicity 3, and 1 with multiplicity of 1. Okay, so those are our zeros. Then we also need the y-intercept. And the way we do that is we actually just look at these numbers here, the last few numbers. So I'm going to do negative 2 to the 4th power, which is 16, 1 to the 3rd power, which is 1, and negative 1. And I'm going to multiply them all together. So 16 times 1 times negative 1 is negative 16. So that's my y-intercept. So here's what I have so far. Okay, so here are my zeros, and I abbreviated multiplicity with MULT. Okay, and then here's my y-intercept. That's the work we just talked through. Next, I need to investigate these limits as x approaches positive infinity and as x approaches negative infinity. And you may recall doing this when we talked about end behavior of a function. Remember, we look at the leading coefficient, which will be x to the 4th times x to the 3rd times x to the 1st, which is x to the 8th. Okay, so let's write our end behavior out like we used to do in pre-calculus. Okay, so what I did is I wrote my leading coefficient down. That's supposed to be x to the 8th. I don't know why I typed a 4 there. It's an 8. Okay, so x to the 8th is my leading coefficient. Now notice it is positive. So as x approaches positive infinity, my function is approaching positive infinity. Now this power was even, meaning that this f of x sign has to match what's going on when x approaches negative infinity. Now, writing this as limits, you'll get this. As x approaches negative infinity, f of x equals positive infinity. And as x approaches positive infinity, f of x equals positive infinity. Okay, so that's what it is in terms of limits. Who knew that we were doing limits last year in pre-calc? So the last thing I need to do is graph this. So I'm just going to make a little room here and put the graph up. Okay, here's the graph I got. Okay, there it is. Now notice the even multiplicity means that it is touching the graph and bouncing back. The odd multiplicity means it goes through the axis. Okay, and see it's approaching positive infinity in both of these spots. Okay, so that's my graph. Okay, so that's it for this video. Let me know if you have any questions. I know infinity can be a hard concept to think about, so I'm sure there will be questions. And don't forget to do your homework. Have a great day.